So in this video, we are to solve the given initial value problem, and we are given first order linear differential equation, which is x plus 2 times dy over dx plus y is equal to ln of x given the initial condition y of 1 is equal to 15. So the first thing we're gonna do is rewrite this into a standard linear form, which is dy over dx plus p of x, y is equal to qx. So this is the standard form of a first order linear equation. So we want this here isolated, and we want p of x here. These two should be functions of x. So what we can do is divide both sides of the equation by x plus 2, which eventually cancels this one, so we would be left with dy over dx plus y times 1 over x plus 2. We have 1 over x plus 2, y is equal to ln of x times 1 over x plus 2 is ln of x all over x plus 2. So now this is the same as our standard form. So we can actually see that this here is our px, and this here is now our q of x. So our px is this one, and our qx is this one. So the next thing is we will find the integrating factor that we'll be using to multiply to both sides of the equation, and so that we can isolate the y and solve for the initial value problem, solve for the solution. So the formula for the integrating factor is mu of x. The integrating factor is mu of x is equal to e to the integral of p of x dx. But you can notice here that our px is this one, so we're going to plug in that 1 over x plus 2 here dx, and the integral of 1 over x plus 2 dx is just the ln of, and we'll use absolute value here, ln of x plus 2 plus c, but we'll be omitting the plus c here because we won't need it. And mu x now is e to the, so this one here is this one, so we're going to plug in that one, ln of x plus 2. So basically you have x plus 2. So why is this one x plus 2 just x plus 2? Okay, let's say y is equal to e to the ln of x plus 2. We can actually apply ln to both sides of the equation. We can apply ln here, ln of here, and we can bring this down according to the rules of logarithm ln of e. And as you see that ln of y is just equal to ln of x plus 2, since ln of e is just equal to 1. Okay, so our y is now ln of, no, not ln, y is eventually equal to the absolute value of x plus 2. See, and y actually is our mu of x, so our mu of x is just x plus 2. So we won't be needing this. Okay, so after finding our integrating factor, we proceed with multiplying this x plus 2. We will be using this to multiply to our original differential equation, and we can actually isolate our y, and we can solve for the actual solution. But first, we will need to get rid of the absolute value because it will be easier. We remove the absolute value since this here is can't be negative. This can't be negative. X plus 2 is greater than a 0 is always positive. Always positive for values greater than negative 2. So for x is greater than negative 2, mu of x is just x plus 2. Okay, so we use x plus 2 here. So let's go delete this. And let's go use our integrating factor. So a differential equation, remember, is dy over dx plus 1 over x plus 2 times y is equal to ln of x all over x plus 2. So if we multiply x plus 2 to both sides of the equation, we'd go back to x plus 2 dy over dx plus y is equal to ln of x. And as you can notice here, we can actually express this here, the expression on our left hand side, as d over dx y times x plus 2 is equal to ln of x. So let's go explain why is that. And the reason is, take note that d over dx is of y times x plus 2 is just when d over dx, let's say uv, these two variables when derived in terms of x, it says u dv over dx plus v du over dx. See? And if we derive this one, so this would be t over dx of y is dy over dx, and d over dx of x plus 2 is just 1, right? Plus, no. We copy the x plus 2 plus derivative of this one. In terms of x is just 1 times y. So see, this is the same thing as this one here. X plus 2 dy over dx, y. So basically, this is true. So we'll put that one. Let's delete this. So now that we have that one, we can actually integrate both sides of the equation in terms of dx. So we now have this one can cancel. Y times x plus 2 is equal to integral of ln of x dx, right? Because this is in terms of x. We're integrating ln of x in terms of x. So let's go integrate ln of x dx, and we're going to use the integration by parts. Integration by parts. So we'll let u is equal to ln of x, and let dv is equal to dx. So integration by parts is derived using this one, d over dx uv again. It's equal to, again, u dv over dx plus v du over dx. So you can actually multiply dx here and take note that uv duv is equal to udv plus v du. So now u dv is just equal to, let's go integrate these, we can actually, is equal to integral of duv minus integral of v du. So udv, integral of udv is actually uv minus integral of v du. That's how we prove, or how we derive, the integration by parts. So now we assume that our u is this, u ln of x, and our dv is just dx, okay? And we'll use this uv minus integral of v du. Let's go delete this. So how to solve this? You remember the formula? ln of x dx is just u times v. Which one is v? After integrating this is just x, right? So u times v, we just have u times v, we just have ln of x times x. So this one's l, x ln x, minus integral of v, which is x, du. And du is just 1 over x dx. So let's put that one here. So u times v minus integral of v du. So this is just x ln of x, integral of, cancel these, we have dx. So x ln of x minus x. So we don't forget the plus c sign here. We'll just put that here because we can't see those. So this is the answer for this one, integral of ln of x dx. So see, we have this. Let's go delete this. So y times x plus 2 is equal to integral of ln of x dx. This is our answer, right? This is integral of ln of x dx. So we'll put that one here, minus x. We're looking for the value of y of x. So we can actually divide both sides of the equation by x plus 2, or multiply by 1 over x plus 2. So we'd be left with y in the left hand side of the equation, and we would have 1 over x plus 2 times x ln of x minus x plus c. And we're going to use the initial condition, y of 1 is equal to 15, to find the value of c. So y of 1 is equal to 15. This means that if the value of x is equal to 1, the value of y is 15. So we're going to plug in the value of x here as 1. So 1 over x plus 2 is 1 plus 2. X is 1, ln of 1 minus 1 plus c. So 15 is equal to 1. 1 plus 2 is 3. ln of 1 is just 0 minus 1 plus c. So multiply this by 3. We'd get 15 times 3, 45 is equal to negative 1 plus c. So plus 1 to both sides of the equation, we get now 46 is equal to c. So we have our y as 1 over x plus 2, x ln of x minus x plus 46, which is the same answer in here. So the question is, give the largest interval I over which the solution is defined. So obviously, we're just going to look for the interval which makes our solution defined. So that means, so there should be some restriction over here that this denominator x plus 2, so anything divided by 0, you remember, anything divided by 0 is undefined. So what are the values of x that will make the denominator x plus 2 0? What are the values of x? X is equal to negative 2, right? So x should not be equal to negative 2. This should be part of the domain. X should not be equal to negative 2, because if this is negative 2 and negative 2 plus 2 is just 0, and we can't divide anything by 0 because this would be undefined. So that's one. That is one. Another would be this one, ln of x. ln of x is undefined for negative values of x and 0. So basically x should be just greater than 0. All of the positive real numbers. Okay, so now the domain should be 0, infinity. So since negative 2 actually is not included here, so we can actually neglect this one. So we will use this as our largest interval over which the solution is defined. We will not include the negative numbers. We will not include 0, because if 0 is included, then this will be different, but 0 is not included in our intervals, so this is correct. So that's it, I think. Thank you for watching my video.